Hope you got some cold tea or warm coffee. So part B, I'm going to split up into two. Bit of a complex question what they're actually asking for. So determine the percentage error introduced in the computation of the maximum stress by assuming the bar is straight for these various cases. So what it's saying is, let's imagine we don't have a curved bar. And we're going to replace it with one that's been straightened out. So that leads to the question, how are you going to straighten out? But not really, because we're not really interested in the length of the thing, because we're not applying a force downwards, even though it looks like it. We're applying a turning moment at the end, or a bending moment at the end there. So however far out I am, that's not going to change things in terms of the amount of bending stress that's being caused on this side and this side. In principle, make it too close, then you can't imagine that you get uniform stress behaving through the bar. So for this, you need to go back to the engineer's bending equation. And we're going to use that. So looking at the end of the bar, we've got this being pulled in this direction and squashed in this direction. Got the symmetry plane, an axis down the middle, 20 millimeters to get to here. So to find the stress, we've got my, the contraflexural equation. I is, just have to be careful what's our B and what's our D. So notice that we're trying to bend it around this axis here. So this axis here is my B, or this length here is my B, and this is my D, my depth, that I'm trying to bend it. So 1/12 BD to the power 3. So that's all I'm going to do for the first part, is just work out what the stress is, assuming that it was a straight bar. So let's make sure we don't make any silly mistakes this time, working SI units. The bottom 1/12. We got a B of 60, a D of 40, and work that out, and you're going to get 7.5 megapascals. Okay, so that's what we just want to do for the first bit. And the next bit, which becomes a bit tedious, we're going to compare this result with these various results where we're going to have different curvatures. So 20 millimeter curvature, 200 millimeter, and then 2 meter curvature. Obviously, what we're trying to show here is make this thing more and more curved, and we're not changing the amount of bending. In effect, we are becoming more and more straight. So the longer our radius of curvature, the more I'm expecting this to agree with this bar being approximated as modeling as if it was a 7.5 megapascals. Okay, I haven't hit the 5-minute mark, so actually I will carry on then and do this. So for this, we want to go back to part A, and we just really want to grab, don't know if I can, grab one of these. And reuse this. Actually, it's tidy it up. So the values that I'm changing are the R bit. C, it's saying maximum stress. And the maximum stress was caused by this one here. Yeah, so the maximum stress is caused by the compression. So for this case, we put in 15, 15. So all we have to do is, in that equation, put in these numbers each time into my other equation. So for case A, we're going to put in 20. For case B, we put in 200. And then for case C, we'll put in 2000. It's a bit tedious, I don't want to write it all out again. So 200, 2000. Notice I'm working in millimeters. So I've got my 10 to the minus 3 there. 200 goes in here. 2000 goes in here. I cannot be bothered to do the calculations, so I'm just going to quote them. And the calcs are, for this one, very similar to our previous result. So our previous result was minus 12.5 megapascals. Actually, let's correct these things. This is B and this is C. And this time it is minus 11.43 megapascals. This one here is minus 7.98 megapascals. And this one here is minus 7.55 megapascals. And as you can see, compared to if we imagine this to be a straight beam being twisted, where we have 7.5 megapascals, but minus there, so it's a compressive. The longer you make your beam, the more you're tending towards this number. The percentages work out to be 34% disagreement, 6% disagreement, and 1% disagreement. Okay, so there we go. I'm not going to do the calcs, just assume that I've explained it all correctly. We've got the numbers up there. Alrighty.